So perhaps I should start because I see that we are already many participants. I think everyone is around. So let me welcome everyone to the quantum optics course. As I already told you, the only requisite that I ask of you is that you know quantum mechanics. And please, it's very important that you go to the lecture notes and you read through this introductory chapter that is the basics, the very basics that we will use of quantum mechanics, but also you go to Appendix A of the lecture notes that contains a review of classical mechanics, of algebra, and of quantum mechanics that is very detailed, even if it is a bit compact. Today, we will have a short lesson. As I already told you, it's only 30 minutes. So what I plan on doing is I will introduce some organization about the subject, and then we will dive right into just elementary quantum mechanics. I will remind you a few things about quantum mechanics. Let's start with quantum mechanics with pure states. What I will do here is I will just give you, in a very compact way, in a very summarized way, the axioms of quantum mechanics, one after another, in the way that we are going to exactly use them. So first of all, there is one foundational axiom in quantum mechanics, which says that in quantum mechanics, any system is described or is associated with a Hilbert space. So we will always denote Hilbert space with a calligraphic letter, usually a calligraphic H, like this one here. And what's important is that you remember that Hilbert space is essentially a vector space. And we will always denote vectors with this ket notation, bracket notation, that you are already familiar with, hopefully. And it's a vector space in which we have defined an inner product. An inner product, it's simply something that takes two vectors, and we will denote it like this. We take vector phi and vector psi, and we have an operation called inner product that creates a complex number, okay? So just having these two things, vector space and inner product, that's already a Hilbert space. When we are talking about finite dimension. For infinite dimensional vector spaces, we need to add one more constraint, one more condition, which is that the vectors need to be normalizable. Which means that their norm needs to not be infinite, okay? So this is a Hilbert space, and as I said, every system in quantum mechanics can be described with the proper Hilbert space. Now, how do we describe states? So in quantum mechanics, the state of the system is specified by a vector in the Hilbert space, but not just any vector, but a vector that has unit norm. So we have to normalize to one the states, and you will see why in a second. Then the other important thing is observables. So imagine that we are interested on measuring or understanding the physics of one specific observable that I call A, okay? And we know that experimentally we can measure it in some way. So in quantum mechanics, in the mathematical formalism of quantum mechanics, every observable is associated with a self-adjoint operator. Self-adjoint operator, which means that the operator is equal to its adjoint or Hermitian conjugate. And what's special about self-adjoint operators is that they have a real spectrum, they have real eigenvalues, and also that the eigenvectors of the self-adjoint operator form a basis, an orthonormal basis of the Hilbert space. So this means that using something called the spectral theorem, or just the spectral decomposition of the operator, we can write the operator in this way. And there are many important things in this expression. So the first one is that this D is the dimension of the Hilbert space. The second thing is that these objects here, which are these A's that are the eigenvalues, as I said, they are real. And finally, these eigenvectors, I said that they are a basis of the Hilbert space. So let me write it like this. So this set of eigenvectors, they form a basis of the Hilbert space. And by being a basis of the Hilbert space, what I mean is that first of all, they are an orthonormal set, as I already mentioned. And they form a resolution of the identity. So they span the identity in this way. Okay, so this is very important because once we have a resolution of the identity, we can now take this, we can take this identity, this expression for the identity, apply it onto the state of the system, and we get what is known as the representation of the state in the basis A. So in particular, if we do this, what we get is an expansion of the state in the basis of the operator, the eigenbasis of operator A, with some expansion coefficients psi j that are nothing but the inner product of the basis states, the basis vector, sorry, with the state. Okay, so I hope this is clear, but I already have to make a few remarks about this. So the first remark is about what happens when we go to infinite dimension. So in particular, when the dimension goes to infinity, it can happen that there are self-adjoint operators in this infinite dimensional Hilbert space that have eigenvectors which are not normalizable, which means that they don't live in the Hilbert space. So specifically, imagine an operator Y that has a continuous spectrum, okay, of course, of real eigenvalues because it's a self-adjoint operator, and with eigenvectors Y and eigenvalues Y. And what's important is that these eigenvectors Y are not contained in the Hilbert space because they are not normalizable. So this is something that can happen in infinite dimension. And you might wonder, why do we even care about these operators if their eigenstates are not vectors in the Hilbert space? Well, we care about them because still, sorry, we can actually do the following. So we can use these eigenvectors as a resolution of the identity. So we can expand the identity in these vectors which are not part of the Hilbert space in this way, provided that we have normalized them with the so-called Dirac delta normalization. And this is something that will always be possible for self-adjoint operators in infinite dimensional Hilbert spaces. And then once we have this resolution of the identity, even though these guys in here are not vectors in the Hilbert space, we can use them to build a continuous representation of the state of the system, because we can take the state of the system, apply the identity in the form that I wrote above, and then we get now oops, we get now a continuous representation, because now this function or these coefficients psi of y, which are still the inner product of the eigenvectors with the state, now they form a continuous set, which means that they are a function, a complex function of a real variable y. So we will talk a lot about this kind of representations during the course. So I will not say anything more for now. The next remark I want to do, which is half a remark, half a postulate, okay? It's that I told you that observables are represented by self-adjoint operators in quantum mechanics, but I actually didn't tell you how to build them. So if I know that I want to measure an observable in the lab, how do I build a quantum mechanical operator associated to it? So I want to give you one prescription that is very useful, that it's the following. So let me call it the classical to quantum observable correspondence. And what this prescription says is the following. So when we say classical system, what we mean is that the system is completely specified by a set of generalized positions and momenta. Okay. Then this is what we learn all in, let's say, classical mechanics. Then in classical physics, an observable, so a classical observable, it's nothing but just a real function that depends on these positions and momenta. Okay. So this is a real function that depends on positions and momenta, and every function like this, it's an observable that in principle we can measure in the lab. So then for cases in which we have this classical observable, we know what is the classical observable, we have a prescription. We have a prescription which is the following. The prescription says, first, take that classical observable and do something that we call symmetrizing it. So we symmetrize A and we turn it into something that we call the symmetric form. And I show you in a second what it is through an example. So the example is the following. So imagine that your classical observable is this function here, pq squared. So now classically, I can write pq squared, or I can write qpq, or I can write q squared p, and these three forms, so these three orderings of p and q, all lead to exactly the same observable. So when I say symmetrizing this observable A, I mean that we write all the possible orderings and we weight them with, in this case, with 1/3, because we have three orderings. And this is what we will call the symmetric form of A. Okay, so given this symmetric form of A, let me move this a little bit away. So given the symmetric form of A, the prescription says that the quantum mechanical operator, it's simply the symmetric function, so the symmetrized function, now replacing the position and momentum classical variables, but position and momentum operators. And what defines these operators is that they obey something called canonical commutation relations. And I'm sure that you are all familiar with these relations, but let me write them down. So these relations mean, this is just a postulate, it's an axiom. So this is what we have to do in quantum mechanics. We change position and momenta by position and momentum operators that satisfy this kind of algebra structure, in which positions and momenta do not commute when they are of the same degree of freedom, but they commute, so the positions with themselves commute, and the momenta with themselves commutes as well. Okay, so it's very, very important that you keep this in mind. Okay, and this is essentially going to we are going to use this through the course all the time. Okay, so you will get very, very familiar with this algebra and what you can do with it. Okay, so let me then move on to the next postulate. So the next postulate is regarding the measurement of observable. So imagine that we measure an observable A. So measurement of A. So we are interested in the laboratory on measuring an observable A with self-adjoint operator A. Then what quantum mechanics says is that in the lab, you can only observe eigenvalues of this operator. That's the only outcomes that can come in an experiment where you measure A. In particular, you cannot even know for sure which eigenvalue will come. So you know that one of the eigenvalues AJ will appear, but it will appear with some probability distribution. So in particular with probability PJ, that is just these expansion coefficients that I mentioned before, the square of them. And this is known as the Born rule. It's another postulate of quantum mechanics. And it's very interesting because it simply says that not all the possible real values of A are available, only its eigenvalues. And then the next postulate related to this one, it's very, very important as well, and it has come with a lot of conflict in quantum mechanics that maybe someday we can talk about. And it's the following postulate. It says that after the measurement, so after the measurement, what happens is that if the system was in state psi prior to the measurement, then after the measurement, if we have obtained eigenvalue AJ, then the state collapses, so changes automatically to the state AJ. And this is known as the collapse postulate. Okay, and it's very important because it introduces in quantum mechanics something that is known as irreversibility, because once you have measured and you have gotten the eigenvalue AJ and the system collapses to state AJ, you cannot do anything to come back to the previous state. That's what you get. If you want the system to be in the previous state, you have to know what state was that and prepare it again in the lab. But you cannot undo the measurement. Okay, then associated to measurements, there are a couple of statistical quantifiers that are important. These quantifiers allows us to kind of summarize what we expect when we measure A with the system being in some state psi. And they are the following. First of all, something that we will call expectation value of an operator A, that it's simply this object here. So if the system is in state psi, we simply take what we call the expectation value of the operator A in the state psi, which is this sandwich with the state. And what's important is that you can show, you can see in the notes, that this coincides with what in statistics would be the mean. So if we prepare the experiment many times and we measure the observable A many times, the statistics of the outcomes in the experiment will follow this mean value. Then the second object I want to mention is what we will call the variance, that is defined as this. So the expectation value of the square of the operator minus the square of the expectation value. So as I said, this we call the variance. And what's important about the variance, it's actually that it allows us to define something that is just its square root, that we will call uncertainty. And it provides the spread of the outcomes in the experiment around the mean. Okay, and once we have defined this thing, then I can give you one consequence of quantum mechanics, which is known as the uncertainty relations. And what the uncertainty relations say is that if I have two observables, A and B, then this product, so the product of uncertainties of A and B in some state of the system, it's always, so it's lower bounded by something that is proportional to essentially the expectation value of the commutator between the corresponding quantum mechanical self-adjoint operators. So this is an incredible consequence of quantum mechanics. This is not a postulate. This can be proven, as you probably know. And it's an incredible consequence because it says that in quantum mechanics, we cannot prepare states psi, okay, in which we can predict with certainty what will be the outcome of a measurement of two observables, A and B. Or in other ways, we cannot create a state of the system in which all observables are well defined at once. That's impossible in quantum mechanics. And we will also talk about this plenty during the course. So, and then finally, let me take maybe 5 more minutes to tell you the final postulate of quantum mechanics, which is related to what happens to the system when we let it evolve without measurement, okay? So we just let the system do its thing. So it evolves in time. We prepare it in some state initially and we let it evolve. So this is what we will call unsupervised evolution. Unsupervised evolution. And in quantum mechanics, unsupervised evolution is equivalent. So again, this is a postulate. This is an axiom of quantum mechanics to something that we will call the time evolution operator. That can be written as the complex exponential of the Hamiltonian times the time divided by IH bar. So, and what is this operator H? This operator H is just the Hamiltonian of the system. So for time-independent systems, such as the one I am writing here, but everything can be generalized to time-dependent Hamiltonians, just with a little bit more of notation. For time-independent Hamiltonians, this operator is simply the observable related to the energy of the system. And well, in classical mechanics, you know it very well from Hamilton description of classical mechanics. And essentially, you can take that Hamiltonian and turn it with the prescription that I gave before into a quantum mechanical Hamiltonian. Or maybe if you have some degrees of freedom that are purely quantum and have no classical analog, then you have to find it based on empirical observations and maybe symmetry principles, so theoretical arguments, reasonable theoretical arguments. But in any case, unsupervised evolution, it's equivalent in quantum mechanics to this time evolution operator. And in particular, we will have two alternatives to describe evolution with this time evolution operator. The first alternative is what is known as the Schrodinger picture. And the Schrodinger picture is a picture in which what we have is that the state of the system is evolving. So states evolve in time. So states evolve in time. And how do they evolve in time? They evolve in time simply by applying the time evolution operator onto the initial state. So if we prepare the state of the system in some initial one, then we apply the time evolution operator and we get the state of the system at a later time. And in this picture, operators stay fixed. They do not evolve in time. And if you prefer the differential form of this expression, you can take the time derivative and you will get something that I'm sure you are familiar with, which is known as the Schrodinger equation. Okay, but as I said, there is another alternative. Instead of using this Schrodinger picture, so instead of states evolving, we can use something known as the Heisenberg picture, in which now what evolves are operators. So now operators evolve. And states remain fixed. And the operators evolve in this specific way. So we apply a similarity transformation, this, as it is known in algebra, with using the time evolution operator, which is a unitary operator. So in particular, what we do is that if we start from some initial operator A, or in general operators A, then we apply this U dagger U, and then we obtain the operator at a later time t. And again, this has a differential form that is known. So is this form in here? Oops, sorry. Let me move this a bit. Which is known as the Heisenberg equation. Okay, and let me just finish by telling you why these two pictures or ways of making evolution in quantum mechanics are equivalent. So the equivalence comes from the fact that when we want to actually evaluate observable quantities, as we have mentioned, are always related to expectation values of operators. But expectation value of an operator means the following, means that if I know that my state is psi, then I have to simply take my operator A and do the sandwich with the ket and the bra psi. This is at a given time, but what happens if I want it at a later time? So I want the expectation value at some time t. Then what happens is that according to the Schrodinger picture, so in the Schrodinger picture, what we have to do is we have to change the state psi initially, okay, by the state u applied onto psi. So then if we do that, we obtain this in here and u dagger in here because we have the Hermitian conjugate for u. So then we see that essentially what we have done is just applying the Schrodinger picture evolution to the state. But if we only care about the expectation value, actually we can see that instead of making evolution onto the state psi, we could interpret this operator here as a new time evolved operator that is precisely the one that I gave you in the Heisenberg picture. So I think that with this, we will finish for today. So thank you all for coming and see you then next week.